thank you to Pascal for accepting this invitation at quite short notice. He happened to be in town and we managed to find the time slot. So that's fantastic. And thanks to everybody also for coming along and looking at short notice. So yeah, very relieved to see what you have to say.
Thank you. Well, thank you for coming on short notice. So as Ian pointed out, I have been doing this kind of stuff for a while, and a lot of it has been about shape reconstruction, 3D shape reconstruction. So to take you back 10 years, get to the top of a Swiss mountain, Matterhorn in this case, throw a drone, and the drone brings back pictures, and you make a map. Okay, this is actually ancient technology. But what happened about 2010 is that it got to the point where it became fully automated. So in this, to produce that 3D Matterhorn, well, there was a bit of manual intervention. Go to the top of the mountain and launch a drone, although truth be told, it could have launched from the ground. Just recover the drone, but the rest is completely automated. The processing of the images, there is no manual intervention at all, to the point where this became a spin-off company. It's called Pix4D, which now was actually is a pretty solid commercial presence. And so the mountain is good, but it doesn't deform, right? We also have a lot of interest in deforming things. So this is also fairly old work, where what we had is a high frame rate video sequence of a baseball. That baseball is shot with a cannon, a special cannon, against a bat. And this is done by mechanical engineers in the Baseball Lab of America in Washington State University in Washington State. And what these people are interested in is modeling the deformation, which, by the way, I don't know, imagine a cricket ball would be the same. These things are hard. And to deform it as much as this one, you had to throw it really hard. And so what we did for them was to take an image. You take an undeformed version of the baseball, which is a sphere, and deform it so that it matches what you see in the image. From this, you can infer the 3D shape, and you can do this over the whole sequence, and in this way, you reconstruct the impact. The point of this exercise, I have no great love of baseball, I must confess, but the people in Washington State are creating simulation software. And they want to check that their simulation software produces something useful, which is reality. And in essence, what the vision does in this case is provide a ground truth. We told them, okay, here is what really happens. Your simulation codes should produce something like it. Okay, so this was then, and what both these examples have in common is that the way we represent 3D surfaces is using 3D meshes, which is, I mean, it's an excellent representation, it works, it has many, many fine qualities, but it also has a few drawbacks. And the drawbacks are, one, the topology of a mesh typically is fixed. Once you build your 3D mesh, you can change its shape, but changing its topology is not easy. And two, these kind of representations are not incredibly deep learning friendly, which in 2011 didn't matter that much, but now it really does. So what can you do? What you can do is look at a different kind of representation known as implicit shape representation or level sets. And I've been given this talk, I mean, this is several ideas, by the way. And I've been given this talk, giving this talk in 1990, which I could have, I would have referred to level sets. And that's with an interesting example that I will come back to. We get told all the time that things move at a frenzied pace, that things change all the time. Yes, and these old ideas have a fairly, if they are good, have a fairly long shelf life. And this is really a good idea. The implicit surface, which is, if we want to define it mathematically, is I'm going to represent a surface, in this case, the Stanford bunny, by defining a function f from r cubed into r. And I'm going to make it so that this function assigns negative values inside the rabbit and positive values outside, which means the surface itself is the zero crossing. So that's why the term implicit, I'm not explicitly saying what it is, but it's implicitly found by finding the places where you go from minus to plus. And a typical function f, which is one that's used often, is a signed distance function. So it is the ordinary Euclidean distance in R cubed, but you make it positive on one side and negative on the other. So one of the beautiful properties of this is now you have surfaces whose topology can change, because the topology of the level set is not fixed. It can change differentially. And this is very, very nice. Was observed in the 1990s, or maybe even earlier, but it didn't catch on then. And it didn't catch on then because how do you represent this function f? The most obvious way to do it is you create a voxel in your a voxel grid in your computer, in your program, and you put values of f in that voxel grid. Problem with that is that it's computationally, I mean, you need huge grids, huge amounts of memory if you want any kind of resolution. It was bad in the 1990s. It's not as bad now, but still bad. So that made it impractical. So very nice math, not terribly useful. But that has changed now. And that has changed now because of deep learning. There are some guys, some people in 4 years ago who figured out that you don't need to represent the cube explicitly. What you can do is instead you use a deep net, actually a fairly simple one. It's just a multi-layer perceptron that takes as input a point in space x and outputs the value of the function f. And this is not particularly memory intensive. You can do this. We do this all the time these days. So you can do this, and you can actually do even a bit more than this, which is you can make the output of your function f be conditional on the vector c. So c is the code, or it's a latent vector, but it means that for this output is now conditioned on c. C defines the shape of the surface you are trying to represent. So this is a very powerful representation, and I'll discuss in a moment how you learn that latent representation. But there's still one little problem, which is, let's say you do need the explicit, you need the mesh at some point. And one case where you may need it is you now want to render your surface, or you want to do computed fluid dynamics, which is what I talked about in the other talk. So I'm going to the people who build wings. You want to do aerodynamics, you need the 3D mesh. And in that case, the normal thing to do is to run marching cubes. Problem is marching cube is not differentiable. It's inherently non-differentiable. So how do you stick that into a deep learning pipeline? So this is something we've looked at. And in fact, what we've realized is the non-differentiability of marching cube doesn't matter. So why is that? So let us say that you have some objective function, some loss function L, that is a function of a mesh that you want to minimize. So in the case of the wing, you want to optimize its performance. So L is a measure of its performance. And that performance is a function of the vertices of the mesh and the facets. So V and is there something I should do?
No, you're right. There.
The loss function is a function of V and F. So when you do a computation, what are you going to do? You take your implicit surface S, you run marching cubes to get V and F, vertices and facets, and then you feed that to F. That's nothing really complicated about that. Where you get in a bit of trouble is when you want to do a backward pass. If you need the derivatives of L with respect to C, the parameters of the surface. So if you need that to do gradient-based optimization or to put it in a deep learning pipeline, you want to compute DL over DC. So chain rule, this is a sum for over all vertices of DL over vertices, the vertices given the S, and S given C. So two of these three terms are no problem. This one, I'm going to assume L is differentiable. This one, not a problem because S is the output of an MLP that's differentiable. The one that annoys us is this one, dV over ds, because V is the result of running marching cubes on S, and that's not differentiable. But is that really a problem? I would argue that no, it's not a problem. You don't care. Why? Because let's say F is a sign distance function. Then you can show that a point on the surface, and it doesn't matter how you compute it, if you change S a little bit, it moves in direction normal to that surface. So you can actually write that dV ds is just a normal, which in the case of a sign distance function, just a gradient. And if f is not a sign distance function, well, it's actually still true. What happens is you have to normalize this formula by the norm of f, the gradient of the norm of the gradient of s, which, by the way, of course, these two functions are differential, are compatible, because if s is a sign distance function, this is. I'll make my slide. I can send my slides if you after that. Okay, so that means that if, just to summarize, if I have an implicit function s that's defined by a latent vector c, and from this I extract a mesh using marching cubes, I can do all of this differential. And here's an example where I start with an implicit function that defines little cow. So we're still a theme of sheep, cows. So we have this little cow, and to it is associated a vector C, a deep SDF code. Now I want to deform this cow. For example, in this example, I'm going to have a cloud of 3D points that defines a different shape, and I'm going to attract it to that cloud. So how do I do this? I use marching cubes to compute vertices and facets. I compute the distance. I use chamfer distance or anything you like to compute distance of those vertices and the facets to the target cloud. I will compute both the distance and its derivatives, and I will do a gradient step to optimize C, and I will train. And here is the iteration taking place, where my little cow turns to a duck. And all this is differentiable, all this is smooth, even though I've changed topology. The little cow is genus 0, no hole. The little duck is genus 1, one hole. As a matter. It's completely transparent. Okay, so one question, and actually this is not going to go too much into the details of this, but this is why I talked about in more detail in the school previous talk, which is why would you mean ducks? I mean ducks and cows. Well, not very useful, but what is useful is if you can compute the drag of something. So what we've shown is that you can train a deep net to estimate the drag of a 3D shape, a car in this case. And which means that we can do drag minimization. We have a code C that defines essentially a car. We have a deep net that predicts the drag of this car, and now this whole pipeline is differentiable. So we can optimize the shape of the car to minimize drag. And we do it under constraint because, of course, we don't want our car to shrink to a point. We want space to put the engine, passengers, whatever. And here is the result of this, which is we start with a car from the ShapeNet data set, an SUV. This SUV has a code associated to it, and we are going to optimize to optimize the aerodynamic drag of that thing. And we get something like this, which is still recognizably a car, but of much lower drag. And this, I'm not going to go into the details today, but this is actually a very powerful idea because it applies to almost any machine, including perhaps a robot, that needs to be optimized to achieve a certain level of performance is amenable to this. So I have mentioned aerodynamics, but I could have talked about heat transfer, for example. When you design electric motors, you want to dissipate the heat. That's one of the problems. And how you shape the cooling channels matters. And if you want to take this to the extreme, this is an example. I will never do this, but I would love to, which is nuclear fusion. Why am I saying this? Because you may have seen a couple of years ago, DeepMind had a really cool article about controlling a fusion beam using reinforcement learning. And they actually did that, the actual experiment in the EPFL tokamak. So there was a couple of EPFL physicists involved in this. And if you read the article, it says, oh, yeah, very nice. And what do we need to scale this up to something actually useful? And one of the things they say, which is a very long list, but one of the things they say is we could change the shape of that thing to make it easier to control. And this, I mean, from a mathematical point of view, I would know how to do it. I can write the equations. And of course, in practice, that thing is worth billions and billions of dollars. You made the smallest mistake, you burn everything. I'm probably not going to do much with that. But instead, and that's what I discussed the other day, we are going to play with little remote control planes, which are worth a few $100 and can crash if we have to. But the idea applies, the same idea. And so I strongly believe that this will has a potential for a real impact in the world of computer-assisted engineering, and we actually have a little spin-off that is trying to prove it. Okay, so that's one thing you can do with it, but now if we go back to computer vision, how can we use something like this? So if you want to publish papers in CVPR and similar places, which is also one of the things you like to do, is single view 3D reconstruction is a big thing. Now, from a strictly practical point of view, I would dispute the usefulness of it because you can always use multiple. But as we know, the viewer is always right. So if the reviewer wants single view, we can use something. And the way we do this is we take an image. We have trained our network to represent chairs in this case. And we first feed the image to a network that will predict a vector C that can represent a chair. So it won't necessarily be very good. We get a C0, which reconstructs this. And then, because our whole thing is differentiable, we can actually optimize so that this reconstructed chair looks more and more like the original, to the point where we get this, but now it really looks like the original one. And just to convince you that it's reasonable, we look at it from a different viewpoint. And yes, it has the right geometry. And this is actually a non-trivial example because of the thin legs of the chair. It actually is a different case. And it works well. So that's good. That got us published. And we can also do something that actually, we can even do something useful, basically enough, which is the idea of going from sketches to 3D things. So the idea here is you're talking to a graphics artist who knows how to draw. So that artist will draw something, a chair, a car. And we can fit one of our 3D models to that sketch. So that's nice because then you don't have to use, you can do that with CAD primitives, of course, but to many an artist, it's actually easier to sketch. And then you can actually modify this very quickly. So for example, we have our 3D chair 3D car. The designer can decide, I want this arm to be lower, or I want the car to be shorter. So just sketch thing. And you can deform it to actually get a shorter car or a chair in which the armrest is much lower. In this case, on purpose, we made the armrest so low that's actually gone. And again, this is the point, is to illustrate the ability to change topology. Okay, we don't want an armrest, we remove it, and we don't make a fuss about it. And this, in fact, has been turned into something that Neural Concept is trying to commercialize, which is this becomes something you give to an artist an iPad. The artist sketches his dream car, and it will produce automatically a car, a 3D car that is conforms to the sketch, but at the same time tries to be aerodynamic. It tries to do the best compromise it can between these two requirements. And actually, this, I think, in practice makes a lot of sense. I have visited a car company, Peugeot, in France, not very long ago. And this actually is a depressing place. Everybody's great. Except one group of people. And this group are the graphic designers. These guys, girls, these people are colorful. They're colorful, they're artists, they know how to make a car look good, but they don't necessarily know about aerodynamics. And And this is a way to give them a tool that they can use to produce cars that are both beautiful and aerodynamic.
Can I throw, excuse me, throw a question in along the way here? So I get how you can train a 3D shape from a single image, you have photometric loss. Give us a hint, how do you train something that you're going from a sketch?
So this, we also have a photometric loss for the silhouettes. So the contours define the silhouette of the car. So there's a photometric loss. And then there is, on top of that, the aerodynamic loss.
Okay.
And in this case, very simple. We just optimize a weighted sum of these two things.
So how about finer objects?
So just a second.
Finer objects, if you want to reconstruct that. So for example,
Okay, so
bacteria or something from the
right, in theory, the implicit shape representation has infinite resolution. So you can be, in theory, as fine as you want. In practice, it's not true, of course, because we trained it on the database. So the fineness of what you can do is basically what do deep nets do they interpolate? So if you have a bunch of cars you use to train your thing, anything you're going to create is some average of all these cars. So it won't be, it's really constrained by the fineness of the database you use to train them. And I'm going to go back to that in a second, because of course, this car, okay, it's nice, but you can build it. I mean, the wheels are touching the body. This car is going to go. And this is no good. I mean, what we really in our dreams, what we want, something that it produces a 3D model, you 3D print it, you're done. We're not quite there yet. So I think there was another question.
As well, so you talked about the database. On the previous slide, you showed chairs and cars. Are these two separate databases or
Yes,
kind of objects?
yes. I
specific
realized
object
that
classes,
I
or-
forgot that slide that somehow I have it somewhere. Let me go aside to
So I'm thinking,
this.
how broad can the class of objects be? Because you can
Not too broad.
you can optimize to do some kind of object recognition as well, right? If you could actually find to see the best matches an object, but you would need a
You could, but I think in engineering context, you would know what you're looking for. So typically, this is, sorry, I forgot that particular slide. I should have had it, which is how do we learn that particular representation? Many ways can be used, but the one we like is, it's called an auto-decoding approach. So we have a database, in this case, the ShapeNet cars. And we have this representation with the implicit surface conditioned by code C. And auto-decoding means you don't have an encoder, just have a decoder, which is what's represented here. And at training time, what you do is you optimize the weight of the network and the code at the same time. So you compute a code for each one of these cars, and you compute the weights of the network at the same time, so that all these cars are represented as well as possible.
So
and that was saying, what I was trying to tell you, which is the quality of the representation is essentially going to be that of the database you use to train. So to your question is how broad can it be? I don't really have a formal answer for that, but my suspicion is not that broad. So, okay, you have a network with infinite capacity and infinite computational power to train it. It could be very broad, but we have neither of these things.
The code. You have this database. Is it you're treating this in the training process? This database, these are treated as images or as meshes, or what's
Meshes.
meshes?
3D objects. There's no image involved.
Uh-huh.
It's purely geometry.
So it's a geometric chamfer loss that tells you if
Yes,
you're close
yes,
or not.
Yeah, yeah.
How do you pick the scale of your your SDF? You've got to pick how many bins you have, or is it multi-resolution?
Seriously, seat of the pants. The vector itself is 256. The C vector is size 256.
Sure.
And it seems to work. It's about as good as
So that's C, but the SDF that you're building out of it, that neural network's job is to
Right.
build.
How big is it?
Yeah.
I don't remember the numbers. It's not that big. It's really an MLP with, I mean, I can go dig up the exact numbers, but it's nothing. I mean, it's not ChatGPT, right? It's a small thing.
Sure, yeah, and that's my anticipation, like looking at the nerf representations and how ridiculously compact they manage to be
I
while
mean,
making these really high fidelity.
right. So we are in the same operating range.
Very cool.
So just coming back to the scale, so apparently the scale does not matter. So even
No.
from the trainings that you.
No, it doesn't, because in say for CFD, it doesn't matter really, because we're going to make the 3D models a scale, and everything will be at that scale.
So
And
everything needs to be at the same scale.
they're all the same scale in the database, yes. They're all normal. I mean,
they
in the
have-
real thing, they're all normalized, they're all the same scale, and they're all the same orientation. So that we don't worry about that.
But-
Because if it had to learn, say, orientation scale, then we would need a more complicated network. It could, in theory,
So
but
that's my question.
Hmm.
Can it be?
it can in theory, but you are making the life of the network harder for no particular gain. So, I mean, in a sense, and I'll get back to that, it's when you can model something with good old mathematical equations, do it. And only go to the network when you can't. Okay, so where were we? We were on the interactive design, okay, of the cars. And I'll get back to that. But what is not satisfactory about this is that this car cannot be built. And we are going to, I'll get back to that. One other thing we'd be looking at is clothes. And one of the problems with SDFs, the way I describe them, is they're great to watertight surfaces. They are no good to model open surfaces, so closed and holes, obviously. There are ways around that. So one way is to represent an open surface, let's say a sheet of paper, by wrapping a surface around it, which can be represented as an SDF. That means you have to give it thickness, which inherently reduces accuracy. So the other option that we'll be looking at is to replace the SDF by the UDF. So just UDF is unsigned distance function, it's just the ordinary distance. And in a UDF, the surface is defined at a place where the function is zero. There's no zero crossing, but there's a place where it reaches zero. So and one of the difficulties in using UDFs instead of SDFs is the ordinary marching cube algorithm doesn't work anymore. Marching cubes expect changes in sign. And we've actually proposed an algorithm that I'll describe in a second that allows us to overcome that and then to fit these kind of surfaces to actual images to get the shape of the clothes that these people are wearing. So what did we do to achieve this? Well, it's actually fairly simple. Let us say that we have a distance field, UDF, And in some square, we have the values of distance U1 to U4. I mean, in 3D, it would be 8. In 2D, it's easier to draw. At every point, not only do you have a value of the distance, you also have a gradient, which is represented by the blue arrows. And in fact, what we did is we can pick one of them, so the first one, and compute a pseudo sign distance by replacing u, which is always positive, by u times the dot product of gi and g1. Which means what? Which means if there is a surface here that goes between the two, these things will agree for opposite directions. So you can do this, and then with some additional technical details I'm not going to describe, essentially turn your unsigned distances into signed ones, and then run the check. And actually, this actually works pretty well, where if you are draping a sweater on this person, if you use, say, an inflated SDF, which is one of the standard ways of doing this, you get interpretation, you get various inaccuracies that completely disappear if you use a UDF. And what this is becoming, this is CVPR deadlines in 2 weeks. So this is actually an image from one of the drafts. And what we are looking at now is what I've shown you was for relatively tight fitting clothing. Question is, how do you handle loose fitting clothing? Which means you have to add to this something that allows the clothes to move a long way from the body, but you have to allow it to do it in a realistic way. So that's where we are with this at the moment. And
I'm sorry. On the previous slide there, so if we take the right-hand figure there, for the simulation, you have kind of 3 different poses. If you look at the skirt in that situation, would that correspond to 3 different values of this C parameter, essentially?
yeah, which essentially all this is conditioned on the pose of the person.
Yeah.
So
can you learn then?
When she walks, she changed the pose. So the deformation field has been trained to understand what moving your leg forward does to the skirt.
Does it learn? Because it's different if you move your leg quickly or slowly, right? Some dynamics in C as well. Is that
in theory?
Yes.
In practice. We'll discuss this next
year. Could be interesting.
My question was on the training data, it says synthetic. So is this all on cloth simulation? Is that what it's trained on? So it's, again, purely geometric.
Yes. Plus, it's purely geometric, but then you have a photometric loss function when you fit into the real images.
So you have a renderer somewhere?
Yeah, yes.
Differentiable renderer?
We have a differentiable renderer in there, yes. Okay, so the other thing, the final thing I want to describe is, okay, I've said that the cars we produced cannot be built. Cannot be built because a real car we have parts, for example, body and wheels. The wheels have to be round, and they have not to touch the body of the car, otherwise it's not really very good. So we've designed a representation that we want a latent vector C that decodes into these various primitives, so that we can do the kind of optimization I've talked about while enforcing the fact that the wheels are round and do not touch the body. Which is a couple of examples here. So just to show you what it can do, here's something that's a lot less glamorous. I showed before, but it's important in this case, called a water mixer. So a water mixer is a device where you at one end you pour two or more fluids. They are being stirred by the helix in the middle, and out here comes something where they're being mixed properly. So when you design something like this, you are going to worry about how you're going to shape your helix, the rotating thing. But you also have to encase it into a tube, which is a cylinder, and you have to have rings at the end that are weatherproof. And when you deform these things, you want them all to deform in unison, so as to guarantee that this thing actually makes sense. So we actually have been working on a more sophisticated version of what I've shown so far, where instead of having one single primitive, which is the SDF, you have a whole bunch of them. Actually, you have three kinds. You have genetic primitives, which is the SDF. We have simple geometry primitives like cylinders, cubes, and what you use in CAD system. And you have what we call assisted primitives, which are, they're not quite simple cubes or simple cylinders, but they're constrained not to be too far away from the tires of the car. And then we have an architecture that essentially takes a latent vector that encodes all of this. So it's a little complicated. I'm not, to be honest, entirely satisfied by this, but our job here is to make this, it works, but our job is to make this more elegant.
So in this context, you actually want to maybe preserve the topology. I mean, previously you were mentioning an advantage is that topology is flexible. Holes can appear or disappear, right? In this context, do you want to fix?
We want, I mean, actually, it depends. Again, it's going to depend how you train it. If all your example in a training database have the same topology, it's never going to change. But in the case of the car, you may have cars with and without ailerons at the back. These are topology changes, and this can handle that. By the way, we've done some computations, and that's a side issue. Don't put ailerons at the back of your cars. They create drag. They may look good, but they create drag and actually slow down the car. Okay, so to conclude on this, so what have I shown? What I've showed is that you can combine implicit and explicit representation so that you get the best of both worlds. And the whole thing is differentiable and deep learning friendly. To do this, a really good tool is the sign distance function is your friend. It works very nicely. And for watertight surfaces. And if you want non-watertight surfaces, you can use UTF, the unsigned distance function. And finally, this the last thing I showed is that formalism can be extended to go from one single shape to composite shapes that eventually will be used to optimize shapes that can simply be printed and built. That's the long term of all this. Okay, and of course, it's involved the work of a whole bunch of people over quite a few years. Thank you very much.
All right, thank you. That's fantastic talk. Already generated a bit of discussion during the talk, which is great. Maybe open the floor for more questions. I'll let somebody other than Don have a go first. Jesse.
Thank you very much. Thank you very much for the talk. You had a slide where you mentioned where you were, I think we were talking about learning the code C, and you were talking about learning it under constraints.
Okay, so I was two things. I'm not learning them under constraint. I'm optimizing under constraint.
So, because I guess I was, because you start with like a actual like mesh representation,
Let me put back the slide about learning the codes. Which is this one. Yeah, so this is the learning of the codes. So what we learn is so that for every one of these cars, we learn from a single car, we learn a vector C, so that S of C is as close as possible to that particular car in terms of the chamfer distance. There are no constraints,
Okay.
and they should be. So this is a whole area of research that has been bugging me for several years now, which is I would love to be able to enforce constraints independently of the data. I would like to say, no matter what C is, no matter what the shape is, I want the wheels are not touching the blade. That's a constraint. Hard constraints. I want to impose it. Honestly, how to do. So we've had a couple of papers on that. And I can send you the thing. You can use something called Krylov formality. Basically, long story short, to do this, you do Lagrangian optimization, which means you have to inverse matrices whose size is number of variables. Number of variables is a number of weight in your network. These are really big matrices. And there are ways kind of around that. But, okay, open problem. I'd love to solve it. I haven't solved it.
Okay, thank you.
Questions, Don? Okay, you get another chance.
Yes, please. So you mentioned a differentiable renderer, and I think it's especially powerful to be able to tie the learning to visual data because it's easy and basically free to measure visual data. It's quite difficult to measure geometry. So can you tell us a bit more about the differentiable renderer and which parameters are you learning? Is it material properties, textures?
So I think in none of these examples do we learn rendering parameters. So it's always we learn purely geometric parameters, and then we have a differential renderer that, the simplest case for the single view reconstruction, the renderer produces a 3D shape. The model produces a 3D shape. We project this. We use a differential renderer to create a projection of that shape into the image, and then we compare that to the actual silhouettes.
So what color is the dress?
So how do we give it a
photometric
color?
How do you get a photometric error without knowing the color?
How do we give it a color? I think we pick the color from the image when everything is said and done.
Okay. So folks have gone back and learned the material
Yes,
properties.
No, we could. We could do something more sophisticated, more nerf-like.
Well, even before nerf, there's just like where's the light and what color is it? And
You mean you want us to do real computer vision? No, you laugh, but this is the problem I'm having when I talk to teachers. You want to. So I sound like I'm on fire for this. Would you please do this? It's kind of a losing battle. But that has nothing to do with the science of it. It has to do with human psychology.
yeah, I get it. But we should believe that would work with this.
I believe it will work, and I believe I will eventually convince someone to show that it works.
Right. Follow-up question to that. You said you can optimize over the condition code with constraints. What kind of constraint, if the code itself is learned with the latest representation, what kind of constraint can you actually put on?
Well, you can say, for example, in the case of the cars, that the passenger compartment cannot, you have to preserve a minimum volume for the passenger compartment, for the engine compartment, constraints, geometry constraints of that nature.
So it's constraints on the output of the network, not explicitly on the code.
Yeah.
Lanes.
It's constrained on the output, so it goes back to the previous question. A far more elegant way would be to guarantee that the output of the constraint is all satisfies constraint, but this is much harder.
I have another question. So in the situation where you were talking about the dress, for example, and I think you said there was a different C, like you learn a different C sort of per situation, and the input might be like the position of the legs for each scene. How would you then, if you took that same dress and put it on a different object, you dropped it on top of like a box or something, so it's the same dress, you've learned that code, you learned that representation, could you then like render what that dress would look like in a completely different situation? Or is it sort of tied to this dress has been like learned while someone is
What
walking?
we have is basically a dress model. So it can be shorter or longer or wider, but it's going to be a dress. And so we have a number of standard garments for which the model we use, typically we take after the fashion industry a way to represent the garment.
I guess my question was, it seemed like when you were rendering or when you were like training those situations, you had your code, and then your input was like what your X is for your sine distance function was the position of the legs. But if it was no longer on a person, could you take that code that you learned that represents how like the material function of that dress and apply it to a different sort of geometric,
To a different person.
yeah, or a different like landscape, like putting it on a table rather than being on a person?
Okay, let's take the dress. I don't have it. So if you want to put that dress on somebody who's actually thinner or thicker, there's no thin or thick parameter in dress. So the straight answer is no. But if you think about what I did in the last thing, is then you want to have these parameters be made explicit, and then you learn them. So the answer is yes. So it's
But it depends on the way you want to represent.
it depends on the way you represent your model when you train.
Yeah, thanks for the talk. Again, on the cars, when you are trying to optimize the shape of a car to minimize the drag, you have some distribution of the cars, and in this distribution you have, like, for example, a car with the best qualities in that sense.
With the best quality.
With the best drag, for example.
Okay, right.
And can it really go beyond that? Can you really optimize a car that you have, given the distribution of the cars, and go beyond the best car in this distribution? And then to follow up, if you have a distribution of your nuclear reactors, right? It's not a really big distribution. So when you said it's a risky,
Okay, so let's get to the car. So the way we envision using this in a real world scenario is you start with a bunch of cars, and deep nets can only interpolate. They suck at extrapolating. So you will take your initial car, you will start deforming it. At some point, you are going to get a car, or you may get a car that's starting to be very different from the ones you trained your network for. At that point, the results become garbage. And it's hard to avoid using current technology, but at least what you can do is have something that tells you, look, I mean, my results are not believable anymore. So to do that, what you need is a deep net that gives you not only the drag of the car, but also an uncertainty estimate on that value. And this is a different talk, but this is something we're working on, which is not only to predict the drag, but to say, aha, this number, I'm not believing it anymore. I need more training. And the idea is when you start, okay, so the current thing is going to kind of move in that space of cars. If it starts going out of it, it has to realize it's going out of it and ask for some more training examples. And that actually is a practical solution, it's just effective.
You have to be able to detect that you're out of your distribution, right? There's an uncertainty estimation.
Right, and so, and we have ways of doing this. So if you want me to talk for another hour.
Johnny?
Thanks for your talk. I got maybe a basic question on the SDFs. So
I see what,
the sign distance function that
yeah.
we use in your model. So it's in my understanding, it's representing the smallest distance that is used on surface.
Right.
And my question is, how did you choose such a surface? Is that
What?
how did you define the surface?
Well, okay, so when you use an SDF or any of this interpretation, what you have is this, conceptually, you have a value of S, these signs, in a whole volume. And Marching Cube is the algorithm that goes into that volume, explores it completely, and looks for all the places where there are transitions. And it does it in such a way that it produces points on the surface that can be meshed. So the answer to your question is Marching Cubes. It's a standard graphics algorithm, it's been around forever. It works.
So it can be arbitrarily.
Yes. You can do it at arbitrary resolution, you can, depending on what you need.
And we can define before the training, before you optimize things. Thanks.
I have a kind of maybe follow up actually before about in the dress case, the dynamics. You kind of said that maybe next year, but it's also, I think, really interesting to think about the case where you have some deformable shape, which maybe the shape of being coded by C, and this might be some control input, like in a pneumatic soft robotics, for example, then you control airflow to the different volumes, and it changes the shape. And this is something you want to do some kind of dynamic control over C to change the shape in some simple way. Maybe could you give us a hint? Is that something that, what's the state of the art on that? Or are you guys working on that? Or are the other groups working on that? Or
I mean, maybe I'm working on that directly, but it doesn't seem alien. I mean, basically, because there's some physics.
you just need time variance.
You can
here, right?
simulate,
Some
so-
model for that. Yeah.
Yeah, what I described is static, quasi-static. Dynamic is interesting, but then simulating the dynamics of, say, aerodynamic or pneumatic things.
Not true.
Not true.
But people do that, right?
They do, but it's, we haven't gotten around to it quite yet. Okay. So I don't need much, 10 years.
Yeah.
Do you mind if I take a picture?
Yeah, sure. Yeah.
Any other questions?
Any other questions for?
While we're doing pictures. I'll use the first. Oh, get Ian in the. Beautiful, thank you.
All right, if there are no further questions, then thanks again.